Okay, so we need to come in, sit down, we're gonna explain our posters. I'm sorry, Tim, I was in your way. So when we come up here and we explain our posters, we tell the class what we did. We tell any ahas that we may have found. We go through that list of questions I printed out so you wouldn't have to remember what all I asked you to do, okay? Slides 9 and 10. And some of you went in a divergent way and you would explain that as well. Some things that you thought about that I didn't ask you to actually do, okay, which is great. And then toward the end, I want Ashley B to share something that she did. Ian's group is going to go last because they have something to share. And Ashley, or Ashley is on the other side of your thing. Well, so these three groups need to go last, but is yours on the first one you did or the second one you did?
The first one we did was B.
Okay, but the thing that Ashley's going to talk about is that from the first.
I just noticed it from like the first two.
Okay, so it's from the first.
Yeah.
Okay.
Yes.
So, so who has A?
We do.
Are y'all ready? Where are y'all?
Right there. This-
Okay. This is A, so let's give them our attention. There should be no sidebars. And I don't tell
Not
them
all
to
at one
talk.
time.
Okay, so speak for itself.
Good one.
Obviously, our images of the first 5 stages of the
Hang
pool
on just a
design.
minute. They did A, which is pool number to number of tiles in the border,
Then we set up our table from there.
Table 1, we counted the borders, tiles, the red tiles, and we ended up with a total of 8. And we continued this process for each of the pool tiles, counting the red ones. We documented our data here. After we documented our data from the pool numbers compared to the tile borders, we found a recursive change of 4 additional tiles. So since we had a recursive, our recursive was there's an addition of 4 additional tiles. It is a thank you, finite change. Finite difference. Finite difference. And then we went and looked to see if we could find, just went back again. Explicit rule. So then we went to see if we could find an explicit rule, and actually she found that if you took your pool number and you multiplied it times 4, added an additional 4 tiles, then you would end up with the total of the border tiles.
After looking at the relationship between X and Y, and we knew that we couldn't just stop at multiplying, we had to add, because you couldn't do, you couldn't have 1 times 8 or 1 plus 8 and then have 2 do the same thing, so.
Okay, let's stop and think about what she just said. She's looking at the relationship between the pool number and the border tiles. And she said that she knew she could not just have 1 plus something to get 8, or 1 times something to get 8. So we can't have just one operation. So it's going to have to be a 2-step rule. Okay, good. Nice observation. Go ahead.
Verbal description, we said at each stage of the pool design, the increase of border tiles is equal to 4 times the stage number plus 4 tiles.
Okay.
And then up here we have our graph. So the bottom we have our pool stage number. On our x-axis, y-axis, we have the number of tiles, and we just.
Tell me why you have the pool number on the bottom, which is the x-axis. Anybody in your group can answer that?
So the reason the pool stage number is on the bottom is that you have control over that. You can decide how many pools you're going to build.
Okay.
And that determines how many tiles you will need in order to build it. You know,
Okay. Nice
By the-
vocabulary.
It's the
So one's
independent.
Which one is independent?
The pool stage number is the independent, and the number of tiles depends on the stage number.
Okay.
And since this can continue, we did not connect the dots on the x and y axis. The other extension that we did is the ratio.
Let's not go there yet.
okay.
That'll be everybody is. Okay, so you said you did not connect the dots, why?
Because this could continue, we could have a 6-stage, another pool, so it could be continuous.
So if it stops, you connect the dots, is that what you're telling me?
No,
It's not continuous.
it's discrete, yeah.
What is discrete?
The,
You said this, so it's a pronoun, what is discrete?
how do you say that line?
The data is discrete
Because,
because you cannot build 1.5 pools
okay,
or 2.5 pools.
okay,
And when you're building, I guess the way we built this, you also cannot have half of a tile.
okay.
All of our tiles are whole numbers.
So the quantities are whole numbers and you cannot divide them into smaller units. So therefore, it's what kind of data? Why when I end with a question mark, do y'all look at me like you don't wanna answer? All of y'all do that. So why, what did I just say? Why is it?
Why is it not just why is it
Because quantities are whole numbers, they cannot be fractional.
Sorta. You said it right the first time. The items cannot be, you can't have half a pool, you can't have half a tile. That's what.
Just
It cannot
ask
be
the kids, you ask
proportional.
a question and then I start thinking, I'm wrong.
I know, I end with a question mark and y'all just look at me like, I know I'm right, but what is she doing?
So if we had triangles, could we?
That's a good question, ask
So
the
then I-
group.
What'd you say?
So say, instead of using square tiles, we had triangular tiles, then could we have half, and will we connect the dots?
Are we going to have a triangle?
That's us.
Because you could still have, if
So
this was a
two
triangle,
triangles would make a square.
yes, 2 triangles, but am I
But
still
the
going to
shape
have
is
only one
still-
triangle? That wouldn't be half of a triangle, it would still be one whole triangle.
What if all of them
Good
were
Yes,
triangles?
each
So
of
each
these
are all
triangles,
triangles.
if I put one triangle there, it would be still one whole triangle, it wouldn't be half of a triangle.
Unless we're gonna go into teacher mode now, because
Sorry.
you have a class here that they have questions, so go ahead, you're teacher now.
That makes sense.
She has her hand
Oh,
up.
yes.
So, teacher. Let's say you had, the scenario was you're building a square pool, just like what we have resembled here. We don't have square tiles. And you told us to build them with triangular tiles. To build a square unit,
Yes,
can we have half?
you would not have half of a triangle, because 2 triangles, I'm assuming we're speaking of equilateral triangles, or at least an isosceles triangle.
Right,
A right triangle, okay, so if you have your right triangle, it takes 2 whole triangles to create one square. So therefore, you would not have half of a triangle. You would have 2 whole triangles, but you would have half of a square. This data is contingent on these being squares.
There you
If
go.
it was triangles, then they would still be whole numbers, it would still be discrete data, because for every one square, you would have 2 triangles.
Good question, so what would that do to your border tile, column there?
So the change.
This is this group question.
That would increase that by 2 times the.
Okay, so it would double each of those, because it would take 2
Right.
triangles to
That would
make it.
increase the border tile amount.
Each stage, right?
Okay, alright. Any other questions?
No, that was good.
Okay, so on your list of things you have to tell us about, did she answer all of them? Y'all should be asking those questions if they haven't answered. They said it was, discrete. What's the word if it's not discrete? Continuous. Well, this one is indiscrete, but in mathematics, it's continuous. Okay, what are the other questions on there? I don't think they've answered them all. Rochelle,
What is the rate of change
of,
for the total number of border tiles? I guess, I can't say total number, right? Rate of change.
for, the rate of change for the border tiles, she did say was adding more.
We said finite because it's always.
What's the rate of change?
Finite difference, that's just the name of it. Who knows who named it?
Did not have, we did not specify if there was a slope or not.
There is a slope, the slope would be.
That's a rate
Hang
of
on, I
change.
hear conversations here and conversations back there. I'm gonna blame it on Quentin, even though I really think it's other people.
No, it's good.
Okay, so we're talking about slope. The
But
question is.
isn't that rate of change?
What?
Slope?
You're asking me? They're up.
So slope is a continuous rate of change.
Okay, so
And
it's,
so
it can't
this
be
is also
plus,
a rate of change
but it
like
can't be
this.
plus 4 then.
Okay, so the continuous rate of change is not plus 4, this is the recursive rate of change. It's also a rate of
Okay.
change. Our continuous rate of change is 4 to 1, so for every 4 border titles you increase, our pool stage will increase by 1.
Make sense? If she doesn't make sense, ask her, because she's learning how to explain in really explicit, concrete, clear terms, okay? Not that she doesn't know how already, but it helps to be questioned on how to do that, yeah. Any other thing on that sheet that she has not told us?
Is it
Or they.
proportional? Is it proportional?
Is it a proportional relationship?
Or is it a proportional relationship?
There is no proportional relationship between the number of pool tiles and the number of pools.
How?
I mean,
She did it, there's not, and she, well, I mean,
no, there is not.
how do you know, how many think it's proportional? Y'all afraid to say? How
Yes.
many think it's
Melissa,
not
it's-
proportional?
Melissa, it's
Because
because
I
of your
said change
one
of
rule.
1 and a change of 4. So
Right.
to me, every time you change by 1, change by 4.
So it's proportional?
In my brain, yeah.
Okay, so some of y'all think it's proportional, some of y'all think it's not proportional, how many don't have a clue?
Hold on.
Like not even all the way up.
You have to be honest, because we did cover that this summer, and if it didn't go in, then we have to go over it again, right?
I blame.
Okay. You're out, okay? You're not that, you're blameless. Next one, person. So, we're trying to decide if it's proportional or not. So, does group want to explain, now y'all are teachers at this moment, okay? So teachers have the option of trying to explain it yourself, I don't mean trying, explaining it yourself, or getting the class to explain, are y'all listening? By asking questions. So, if I were the teacher, I would ask questions. There you go.
Jen?
Jen or Jen?
I'm Jennifer, apparently,
Oh,
to
no,
my
I-
tag.
Oh.
My tag says
It's you,
Jennifer
Liquor.
now.
My tag says
It's you,
Jennifer.
because they
This is
So my
contradictory.
question then is. Alright, you win. No, it's a no, yours says Jen. Yes.
Hang on, I cannot hear Jen. Jen is trying to answer this, that Jen.
No, we're still arguing.
Okay? So we're talking about proportionality.
Right,
Is it a
so I
proportion or not?
Well, I heard you say that if you have students who are confused, that you should start asking questions. So my question is, what is proportionality exactly? I mean, what do you mean? Am I comparing these two things? What is that?
You asking the teacher?
Yes.
So when I'm looking for proportional, I'm looking for you to compare 2 different things to see if they're equivalent.
Okay. And so you're comparing,
Then we're
you want me to
comparing pool
determine
numbers.
if the number of pool, the number of the pool is proportional to the number of tiles in the pool, or you want me to compare one pool to another
I
to
want
see
you
if
to
there's a
compare
proportional.
one pool to the other.
Okay, so there's a proportional relationship between one pool and the other.
Can we back up? The definition of a proportion is what? Yeah. Bad question. Who can tell me what that's also a bad question. Tim, what is the definition of
On a graph, no.
No, just in general.
Definition of a proportion is a ratio, a constant rate of change, or a constant ratio between,
Don't look at theirs, just in general.
it's a constant rate of change.
So how would we write a proportion? What does a proportion look like when you write it, Pam?
Could a proportion be described as 2 equal ratios?
2 ratios that are
Equivalent to each other?
So you have to have 2 ratios that are equivalent to have a proportion. So it's gotta be an equal thing in there, right?
Yes.
Of course, some proportions are not equal, so they're non-proportional. If that makes any sense in a math book, okay. So we have 2 ratios that are equivalent. to have a proportion. So one ratio would be tool 1 to 8. The other ratio would be tool 2 to 12.
Yes.
Is that a true proportion? Write them down, ladies and gentlemen. 1 to 8 equal to 2 to 12. This is so important. 1 to 8 equal to 2 to 12. And y'all can, yes, write it up there, please. Equal 2 to 12.
There you go.
Perfect. Are those two ratios equivalent?
No.
Well, I can multiply 1 by 2 to get 2. Can I multiply 8 by 2 to
No.
get 12? So I don't have a scale factor of 2.
2.
I can multiply 8 by 1.5, thank you, I was gonna say something else. To get 12, can I multiply 1 by 1.5
No.
to get 2?
No.
So this proportion is false, right? So is that a proportional relationship? It is not. Yes, ma'am.
So where a lot of confusion is coming in is when you look at a graph, it is being taught, I guess I can't really say unexperienced teachers, but teachers that really don't know, unexperienced, that if it goes through 0, 0, it's a proportional relationship, period. And they're not actually going into depth of why it is. It's just, does it go through 0? Yes, sure, there we go.
Yeah.
And move on, versus actually understanding what proportional relationship is and pulling order pairs or your variables, your ratios together to make, equivalent fractions.
That's a very good point.
So it's more of an understanding and versus just a cheat rule or a trick.
They're not going through that web's depth of knowledge. They're up at the knowledge instead of the depth of the knowledge.
And I was guilty of that at first, until I
So-
really looked at it.
So one of the characteristics of a proportional relationship is if you graph it, it will go through the origin.
Origin, yeah,
It will go through the
But
order
it has to
pair
have two
0,
rules.
0.
linear and show.
It has to be linear and it has to go through the origin. If teachers do not explain the meaning of proportion, then that's something the kids are gonna memorize and forget the next year. And then they're gonna say, I never learned that, they should never taught me that.
So,
Two rules.
Jen,
Yes.
if I were to, say, do a prior knowledge exercise with, whenever we're doing this proportionality, could I pull back to, like in 5th grade, when we do
Ratios.
fractions?
Yep.
Equivalent
When
Equivalent
we add
fractions.
it, equivalent fractions, and would that be a valid connection,
Yep.
of ratios to
Yes.
fractions, that they work the same way?
Proportionality is the ratio that's equal to another.
That's what the
Right,
fractions
and another meaning another ratio given the data. So equivalent fractions is comparing two fractions and seeing if they are equivalent or equal to, or finding an equivalent fraction given
Right.
one. So yes, because you're still finding a scale
Right,
of
so
increase or
it could show-
decrease. Well,
it could kind of provide a foundation
That's
for
a
those
base-
who are like, I don't get it, it's like, okay, remember in 5th grade when you did this?
and actually I make that, yes.
That is a proportional
That's something I
relationship,
say.
right?
Right, but
Okay,
that's
so
a
yeah.
proportional relationship.
Y'all don't use that
just-
vocabulary.
Yeah,
They
the
don't use
word,
it at
yeah.
all, so if their minds are, like, I have no clue, back it up to the.
I actually start out with, I start out with a little thing, hands-on thing, but I make the connection to, remember when we did equivalent fractions in elementary? Oh, yeah.
Only thing is you have to be very careful because these ratios are not fractions. So
No.
you said it perfectly, they work similarly,
Okay,
that's what you
okay.
said.
They're not exact.
okay,
But they're not the same thing, but they do work in the same way,
okay.
which is another reason why kids sometimes get confused. Because
Good reminder.
they're not fractions, but they work like fractions sometimes. So you have to say that over and over again.
Bless you.
Ratio comparisons.
Two.
And that's where the language.
Yeah. So we're not gonna do your second one that you did. Are we through with this? Have we answered all the questions on that sheet for this? So it's linear, which means it is not a curve, right? They've answered all the questions? Alright, now I want y'all to stop right now. This was the very first one. This was A, which is, I'm not saying this to hurt y'all, but it was one of the easier ones to do, right? It was look at all the vocabulary and the depth of knowledge we got out of this with this supposedly easy problem. all because we have them with a public display that they have to explain. If you're not getting your kids up and showing a public display of their work where they have to explain it, not you, they have to explain it, and other people will see things differently or see things in a deeper way and ask questions, then this conversation would never have happened. We would have said, okay, it's linear, those are the numbers, that's the rule, we're done. And you would not have gotten nearly as in-depth as we just did, okay? So public displays keep kids accountable, you know, they have to be able to explain it, and it helps you bring out points that sometimes your kids don't think of, alright? Such as Rochelle bringing up slope. They never mentioned slope until you brought it up. Now Brenda pointed to it, right, in the verbal, in the algebraic expression, but she never actually used the word slope until you did. So does this one have a slope? Yes, it does. It's linear. It has a slope. It has a constant rate of change in the x and the y value. Change in y over change in x. And they're constant. So it has a slope. Okay, thank you, ladies. And leave it up there because we'll do the next one later. All right, so B, yay, you're right. Who has B? Okay, then where are you? I think they're over there. Okay, they have B, so, Ashley, B, tell me what the relationship here, tell me what you're comparing.
The number of tiles in the actual pool,
Let's say it the correct order. The pool number,
sorry, the pool number,
number of tiles in the water.
right,
In the
the
water,
number
okay.
of tiles in the water.
So explain your chart.
Well, first we have the visual, the pictorial model of what we did in the config,
Good, thank you.
and
She's not alone up there, there's three others.
Okay, I do this, so I'll do this part. Okay, so the pool number. Oh wait, that's,
So for pool one,
alright, the pool number, and then the actual pool tiles, so
so we can't see that because it's orange. So for pool one, the water is,
the number of tiles in the pool is. That would be this here, pool, sorry. That's not. Right, so pool number one is
Yes.
here, and the actual number of tiles in the pool is 1. So
Okay.
for pool number 1, we actually have, is that better?
that's much better for old eyes. Thank you. Y'all forget how old
So
I
in
am.
pool 2, we have 4 tiles.
And how did you get that?
Well, I counted it from.
You actually counted it because you're in like third, fourth grade, yeah?
And I went 1, 2, 3, 4.
Good, okay.
So I went to pool number 3, and I said 1, 2, 3, 4, 5, 6, 7, 8, 9. And by this time I started to realize something,
Okay,
that the number of tiles, I'm sorry, the number of the pool actually gave me some information about how many tiles there were in the pool.
okay.
So I started thinking about arrays. With a little help, I started thinking about rows and columns, and I realized that the number of the pool tells me how many tiles are in a row and a column of the array inside the pool. So when I started thinking about that, I realized if there was 4, the pool number was 4, I would have 4 tiles in a row, and 4 tiles in each column, and that would give me 16 tiles.
So you have 4 rows of 4.
4 rows of 4. And so it got pretty simple for me.
Okay, so there are their values. Go ahead. Then, what?
Then,
Oh, I get it. Are we going more in depth on the table or do we go straight to the graph?
It's your explanation.
Okay. What we have here is a well-constructed graph. On the x-axis we have the pool number, 1 through 5.
Mhm.
1, 2, 3, 4, 5, and then on the y-axis, we did the top number at 25, and for one we have, for the one pool we have 1 tile, and then for 2 pools, 4 tiles, 3
Okay.
pools 9, and so on and so forth.
So if it was, we talked about whether that data was linear, we
And
decided that it was not linear,
it's not linear, why not?
Wait, what?
because we talked about this, remember we looked at the graph?
We did this.
Like she's talking to her
But-
husband, we talked about it.
We
I
talked.
told you I was going to.
my big change is,
Go ahead.
well, yeah, it goes 3, 5, and there's a change of 2 in between each of those.
You think the same way as me?
Is there a change of 2 between 1 and 4, Ramesh? Is there a
There's a
change?
change of 3 more tiles, I see,
With that,
That's 3, that's 5.
7, 9, 11.
Okay, you
and
can't
then
tell
if you break
them.
that down, there's a change of 2, it's a constant rate of change of, wait, but it's on the 3rd grade, I'll do that.
Okay, so let's look at what they did. They did something similar to the first group. They found those differences, the changes in Y. And the first time they found the changes in Y, those changes were not consistent, right? So there's not a consistent change in Y. Is there a consistent change in X?
Yes.
Yes, but there is no consistent change in Y. So what does that tell us automatically?
It's not
It is not linear. It is not linear. So, they went out to the next level of differences and they got a constant difference there. So we're looking at the second level of finite differences. And when you go out to the second level of finite differences, that means, and they're constant, it's going to be a particular kind of equation. Quentin, do you know?
No.
How about there? I didn't call your name, you can't be talking. Okay, nobody
you told us
knows
to
there?
talk about, well, you told us to look at this problem like we were looking at it like a 3rd grader.
I did. So
And-
there's third grade.
You know, the rows and columns thing.
It
we were-
multiplies it times itself.
Right.
It does. It multiplies it times itself. Sometimes we call that, I'm gonna have to go get my epoxy so it, talking when I'm talking, or when the teachers are talking, okay? Damn, it wasn't you this time, yay! I love
Well,
Pam.
I mean, we said at the beginning when we were first making it, it's an exponential,
Oh, you used the word exponential, what does that mean?
that it's increasing at, not a linear rate of change, it's going to curve.
It's going to curve, so
The
it is a
graph-
curve.
oh, the
Big,
graph,
big, yeah,
the line.
okay, yeah, he needed to clarify that. So the Y values are increasing at a faster rate than, the X values, that's not what I mean to say. The Y values are increasing more quickly as you go down the chart. They're not at a constant rate of change. The change is much more as you go up, right? So if you go out to 2 levels, 2 finite difference levels, raise your hand if you know what that's called. By the time you get to the second finite differences, what kind of equation, what's gonna be in that equation? Let me get Brenda's, cause you're high school.
You wanted some quadratic equation
Which means,
that it will have the curve shape,
yes, but what does it have in the equation?
a square,
Uh-huh.
an exponent?
It's
Is that
got,
what
and what is that exponent?
It's 2 squared.
It's gonna have a square in there somewhere. If you're out to 2 finite differences, you get the constant change, it's gonna have a squared term in there. X squared, 4x squared, something. It's gonna have a
You
square in
actually
there.
mean also like it's going to have a square.
Yes, thank you, Jen. Because for many, many people, they don't realize that when we say x squared, we actually mean x is a square of x dimensions. X length and x y. So if it's a squared variable, it is a squared physical thing when you have the physical things. It's really hard to explain in good words. I'm not good at this right now. All right, maybe you high school people can explain it better. Anyway, if we went out to the third finite difference before we got a constant there, then what do you think would have to be in that equation, Rochelle? A cube. That's just how it works. Okay?
I think we're
Yeah.
Was that you?
Yes.
Oh, I have my science people over here, so I thought it was one of y'all, and I was
Well, I just didn't do it. I thought it was me, but it was me, but you know.
All right, so going back to this,
this.
they've answered that it is not linear. It's going to be a curve. We don't know the name of the curve yet, doesn't matter to us right this minute. So it's gonna be a curve, and it's going to have a square in it. So what is your rule?
Well, I
We
mean, we
have
came up with a
rules.
few.
Yeah,
What is your
we just
rule?
didn't know how to exactly say it. You said it perfectly though before. Third grade time. It's the
You did say
number
that.
The number of tiles in the actual pool is the pool number times itself.
The pool number times itself. So if the pool number is 1, 1 times 1 is 1. If the pool number is 2, 2 times 2 is 4. If the pool number is 3, 3 times 3 is 9. So it's 1 squared, 2 squared, 3 squared. So the rule is the number of tiles in the actual pool is equal to
The pool number times itself.
pool number squared. There you go. Pool number
I know,
squared.
we were trying to think like third graders, and she goes, I would just say the number times itself.
That's what I said, I was like, they don't know exponents at this point.
But no, no, so that's very good, and I did tell them to think like a third grader, because they were going very abstract on me, and I had to rein them in. Any other questions on there that they've answered?
Is it proportional?
Is it a proportional relationship? Let them answer, it's their project.
No,
Why not?
because 1 to 1 is not equal to 2 to 4,
Okay,
which is not equal to 3 to 9.
okay, so if you're looking at those as, ratios,
Yes.
1 over 1 is not equivalent to 2 over 4, which is certainly not equivalent to 3 over 9. What is happening to those ratios as they go down? 4 over 16, 5 over 25, they're what?
The ratio's decreasing. Or if that's a 1 to 1, that's half, it's a third, a quarter, a
So the
fifth.
quantities are actually decreasing for those other ones. It's further you go down, right? So it's approaching,
They don't never get
Zero,
that.
yeah, it's approaching
it
zero.
will never get to 0, so is it approaching 0? Where is that? Where do we talk about things that approach things before you come in?
Me?
Mm-hmm.
Asymptotes.
Asymptotes. And what grade level?
What?
10th grade.
Way back then.
So if we can plant it in the kid's head that they're approaching a 0, but it will never get to that 0, then when they get to her, that little seed will still be in there. They may not know it's in there, but that little seed of knowledge will still be in there. And then when she talks about that approaching with asymptotes and things, it will not be so foreign to them. They will, somehow it will kick in sometimes. Yes, ma'am.
It'll be like that little dot in the she's making.
There you go. It'll be that red dot that's
Yes.
connecting to 3rd grade. Okay, good job. Anything else that we need to know?
Where's Ashley's right now?
Okay, Ashley had an aha, so Ashley's gonna share her aha.
I had I'm the annoying student, so I don't get it, show me this. So we had, this is where you had 4 tiles, there's pool number 2. And we kept talking in geometry terms, area, perimeter, and whatnot. But the problem with that was, and where I was first trying to do the XY, is it doesn't work.
What doesn't work?
Using terms like perimeter, if I have the perimeter of this, or, because you have your extra tiles, and I can pull them out.
Okay, so let me ask a question.
Yes.
Hold up your first one. There you go. That is the shaded part, the red, purple thing, pink, is, the border around the pool.
Mhm.
Is that the perimeter of the shape, the entire shape?
Is that the perimeter of the inner pool part?
No, okay, is it the
Well, the
perimeter of
number
the
of
inner pool
tiles.
part or the entire shape? Don't answer, Ashley, you're the teacher now. So looking at the pool, just the pool, what would be the perimeter of that pool? Science person, Renee.
So you're asking what the perimeter of the orange?
Yep.
It would be the purple.
Okay, tell me a number.
1, 2, 3, 4. So 4, 5, 6, 7, 8, 9, 10, 11, 12.
Here or here?
She's looking at the orange,
Oh,
and
I
she's.
was looking at the purple.
Yes.
That's,
Water.
hold on now, let's listen to my question. What is the perimeter of the actual
Water.
pool? The water. Lassie Renee,
Oh, the perimeter of the actual water?
the actual water. The orange
2,
water.
4, 6, 8.
And how did you get that?
Because the ones in the corner aren't touching the actual water, unless you technically say that that tiny bit of piece is touching it, but then that's me being too much.
Oh, wait.
So where are your 2, your 4, your 6, and your 8? Where are you
2
getting those?
in the middle of the bottom row, 2 on the
Ashley,
side,
can you point to those as she's doing it?
and then the 2 on the side, or the 4, and then the top on the other side.
Now, Ashley, would you hold up your other sheet? Is that what you mean?
Yes.
So do y'all agree that the perimeter of the actual pool is 8?
But I have a problem.
Hang on, I'm just asking you.
8 units.
Let me rephrase this. Yeah, 8 units. If you were a little ant and you were on the corner of that orange water, okay? When you walk around that orange water, how many units are you going to walk past?
Couldn't you technically, at the very corner of
Yeah,
that
that's what
open, that you slightly touch your butt on it?
But a point, is a point a link?
Oh.
No, point does not have a link. Remember, that's one of those undefined terms? Points have no length, width, or height. Okay, which, I don't know how we can put them together to make a line, but we do.
Microscopic.
Okay, so the perimeter okay, I can say this without asking, do you understand? Which one of those has the purple tiles illustrating the perimeter of the orange water? The one on your left or the one on your right? Brandon,
The one on mine, yeah.
the one on your left, because
Well, I can count and see the, size of the purple that are touching the actual water.
okay, and there are how many?
There's 8.
8. Elizabeth?
So would we consider those tiles the unit measure?
Yes. Yes. So the perimeter of the actual water is 8. So the other one, how many tiles are around the water there? 12. Ashley's aha was that the 12 is not the perimeter of the water, because she, in this one over on my left, she pulled out those corner pieces to show that. Okay, that was her big aha. So the purple tiles have their own perimeter. What is that perimeter?
X times 4.
X times 4?
Except that doesn't work. It doesn't work with 1.
Hey, let's not get confused with the not work, okay?
Okay.
So that's pool what? Pool 2?
Pull 2.
So is it 2 times 4? Is that the perimeter of the purple side over there? That's the perimeter of the actual water.
Well, I was, on this
On
side,
the
I was
left.
saying the perimeter of the purple one, so I was
So,
saying
yeah.
16, so yes, never mind.
Yeah, it's hard because I really need to be over there pointing.
Yeah, I'm getting mixed up. Yeah.
Man, you have too many.
You just need to put a 1 and a 2 on the paper.
I don't know which picture you're
I'm
talking
using
about.
real words, but you can't tell because I'm not right here. Okay. So the perimeter of the orange water is 8, we decided, right? Which is his rule, which was X times 4. The number of pool, the pool number times 4 because it's got 4 sides, right? 8, just the water. This has 12 tiles, is that right? 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, did I count wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Am I right?
Yes.
12. So is 12 the perimeter of the border?
You have to count the site.
No, it's not.
Let people think. How would we find the perimeter of the border, Candace?
Could you use tiles to measure like Ashley did with the inside of the pool?
Tell me how you would use tiles.
So what I would do is line the tiles up on each, of the borders. So,
Did you draw on your?
Yes, absolutely.
She's green. She's being very careful about her colors here. She wants them. That's okay. That's really good. She gets her explanation, then we'll. Okay, I'm gonna hold it up and you explain it.
so. So each of the tiles that I've used represents a unit of length. And so, so that would mean that I would have for each tile would measure a unit of length of the perimeter around the pool border. So I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 units to measure the perimeter
Of the whole thing.
of the pool border.
Okay, so she got 16. Is she right? Because we thought it was 12 a while ago. There's 12 tiles.
We all find the
Yeah.
outside.
Yeah, but you asked the perimeter of the purple.
Correct.
16.
No,
I don't know. There's 16, or, sorry, the perimeter, sorry.
It is 16.
Perimeter is 16.
Okay, we have a science person I want to answer this.
The perimeter is 16, and because the unit of length around each of the sides is totaled to 16, I guess.
Okay, so if you were an ant and you were standing right
Right
here,
there.
you would walk 1, 2, 3, 4,
Right.
5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So she said that exactly correct. Okay. So what do you notice? It's kind of like what's happening over here. What do you notice? What are you pointing to?
It's the same as the equation they have over there, except instead of adding 4, so when I said x times 4, it was correct. I lost my mind when I said it was wrong.
Okay. Okay, so what do you notice about these corner pieces?
They're the same as what was in the pool. I don't know. I don't.
Brandon?
Maybe, I think you're trying to say they'll count it twice before you go in,
Because
because they have 2 sides that
you have to
that
walk
you have
on.
to walk on.
2 sides that you have to walk on. So they are counted twice. So it's 2 here, 2 here, 2 here, 2 here, but then it's 2 here, 2 here, 2 here, and 2 here, which is a total of 16 for the perimeter. You can't tell this with tiles is the perimeter, alright? Everybody's straight on that? And again, we got all of this out of this very, not really calculus problem, right?
You can say simple.
Thank you. We could have just stopped right here. Oh, look, it's not linear. Here's the finite difference. All right, let's go on to the next one because the food is here, right?
Yes.
But I do not want to do that. The food just got here, okay? I do not want to do that because of Ashley's aha. I was thinking that some of y'all may have been thinking the same thing she thought and needed an explanation, and hers is great,
So
isn't it?
I'm just making a comment to get some brownie points here. So though this was a simple problem, it was still rigorous.
Yes, it was. Thank you. Y'all remember our discussion of difficulty and rigorous? What's the difference?
How
Yeah.
deep the
How deep the thinking is. So the problem itself was simple, but the thinking was rigorous. Remember? Remember, let me explain difficulty again. Walking is difficult for a 6-month-old. It is not difficult for you. Once you learn the skill, it's no longer difficult. But it could be rigorous if you're trying to run, I don't know why, but that's a bad example. Yeah, there you go. If you're me trying to walk anywhere fast, that would be rigorous. It's depth of thinking.
The addition to that too, a lot of the students that I teach, they say, I don't get math, I don't understand math, I just don't. But their families and whatnot, they are in construction, landscape,
And they do get it.
and I think whenever you show them this, it's like, okay, so how many tiles of a real world connection? You know, he's building a deck and you have an area of this, but how many tiles are they gonna need to go around or?
To fence the pool so you're not liable.
Right, and what would the fence be, but then if you're to put a border around it to kind of pull it out, cause that's something that